Hi, Charles Martin here with Calculation Consulting. Today I'd like to talk to you about why deep learning works, some perspectives from theoretical chemistry. This is the talk I gave at the MMDS Data Science Conference at UC Berkeley this summer, 2016. The talk was recorded but really hasn't come online yet, so I wanted to just share some of the thoughts and ideas here with you and try to get some feedback. I hope you enjoy it. Let me sort of give you a idea of the structure of the talks or where I'm coming from. I do a lot of talks at the business school at Haas, sometimes at Stanford, and when I talk about data science, I like to talk about the three types of data scientists that I recognize, and I use the analogy from a really fun TV show I like, Big Bang Theory. In the theory, there are three characters. One, Sheldon, who is a theoretical physicist, very, very mathematical, very, well, he's got his own very unique personality. Sheldon is the experimental physicist. He's much more of what I would call the data scientist. He's sort of the more normal guy, has a normal girlfriend, normal relationships, does a lot of experimental work, sort of the kind of typical thing you might see people working in the industry, type of personality. And the other character is Howard, the engineer. This is the guy, typically if you work in a company, probably the one who is going to be implementing things on Spark, trying to get things working in Hadoop. And I give this talk to point out that not all techies are the same, and certainly not all data scientists are the same. And in our consulting practice, we try to hit all three types of problems. We do a lot of fundamental work in machine learning. We just do applied data science, and we do a lot of software engineering. But today's talk is going to be really a talk that Sheldon would give. It's sort of really going back to my days in graduate school in theoretical chemistry and my postdoc in the statistical physics of neural networks, and really trying to take a look at some of these old methods and provide some insight into why they work. So let's get started. What is the problem? Why do we say, what do you mean, why do they work? Well, one of the things that's very confusing about neural networks is that they appear to be at the surface level to be non-convex optimization problems. If we look at this, the section of the expected, what the surface looks like, it's a very, very complex surface, lots of bumps and local minima and saddle points. And generally, you wouldn't expect, coming from a computer science or an optimization background, that a simple stochastic gradient descent solver, a simple gradient solver would work on an optimization problem like this. In fact, most of the problems we've worked on, if you've worked in data science and machine learning for the past 10 to 15 years, have been convex optimization problems, SVMs, logistic regression. Very, very simple problems where any SGD solver will go right to the minimum. And what we're going to find out is that it's been known for a long period of time in theoretical chemistry and physics that, from the context of spin glass theory, that in fact these models do work. There's some really strong evidence to suggest that even though these models appear to be really, really non-convex, in the limit, in the aggregate, in very, very large data sets, they behave almost like convex methods, a type of rough convexity that they have. So we're going to talk today about some of the models that explain why this exists. And I'm going to just introduce some other models which, are sort of competitive and maybe more helpful in understanding today's implementation of deep learning systems. So the outline of the talks, I'm going to begin with a discussion of spin glass models and how they've been applied to deep nets and understanding them. Primarily looking at some work by Lee Kun from Facebook, but also reviewing some very, very older ideas that were understood in theoretical physics, probably in the early 90s or maybe even earlier. Then I'm going to introduce a model, which I think is will be a pretty good foundational model for trying to understand these nets, called the random energy model. And I think I'm the first one to really suggest using the random energy model as a beginning point, a simple mathematical model for understanding networks. And if you think about statistics has the central limit theorem. Think about SVMs, you have the Vapnik-Shreveninkis, the VC theory. I think the random energy model and its variants will be a very good model for trying to understand why deep networks work. And as part of the random energy model, we have some ideas from physics that we have to try to understand. Temperature, for example, is related to regularization. And we're going to have to talk about something which is not that well understood, but very important in theoretical physics and chemistry, called the glass transition. Once we get through that, I'm going to talk about an extended model, an extended random energy model called the spin glass of minimal frustration. This is a model that was introduced as in the concept of protein folding, and it will serve as an analogy for understanding something called funneled energy landscapes. That is, what does the structure of a deep learning landscape really look like? What do we expect it to look like? And then I'll give some examples of what this might come from: restricted Boltzmann machines, from dark knowledge, from adversarial generative nets. So a little warning. When we talk about condensed matter theory, talk about spin glasses and glass transitions and temperatures and random energy models, these are qualitative analogies. I'm not going to try to give very precise mathematical definitions in terms of implementations right now in deep learning systems. I mean, we're looking at a toy model, a mean field model. So we're going to look at the restricted Boltzmann machine. Restricted Boltzmann machine is actually a mean field model of statistical mechanics. So that will probably be the most sophisticated model we'll look at a purely mathematical level. And our goal is to obtain a phenomenological description. In other words, we want to run some simulation using Torch or Theano or TensorFlow, and we want to look at its properties and try to understand when we modify certain parameters like the weight regularization, or we apply batch normalization, or we try to adjust certain temperature parameters in annealing. What does this have to do with why these methods work? So this is a very qualitative, sort of hand-wavy talk to begin with. And then later talks and later blog posts and papers I present will be much more mathematically detailed and really drill into the details of what I mean. But today we're just sort of going to lay out the general conceptual ideas. So the first thing we want to start with is just understand what problem is deep learning actually solving. So if we pose it in this way, we think about how we set up, say, a network in TensorFlow. Usually these are supervised learning algorithms in TensorFlow, although we can do unsupervised as well. But we train them with backprop, and we usually have some model which has some inputs, some hidden layers, and some outputs. And the inputs are xk, and maybe there are some labels. And we try to predict these labels T1, T2, T3 coming out, the class labels, for example. And we may do something like minimize the cross entropy. And so by minimizing the cross entropy, we're trying to train the weights on the network. And this appears to be, it looks almost like we're simply minimizing an energy function, some sort of optimization function. And so that's the first question we ask is, are we just minimizing an arbitrary energy function? Or can we say something more about the structure of these functions to try to understand them? And that's the first piece of the problem I want to look at. In the current understanding, some of the work coming out by Lee Kuhn's group at Facebook of how to look at these models, we look at the neural network as just an energy model. It's just an energy. It's just a function. And this function, we're going to represent as a random function. We're going to call it L for the energy. And we're going to call this the p-spin spherical glass model. This is a very old model. Certainly, it comes out of the theory of spin glasses. It was developed much later. It's an analytical model that can be solved exactly. Has been solved exactly. Can be easily simulated. And the idea is that we just form a simple energy function where xi, the x's are just Gaussian random variables, and the w's are real valued spins. They're just up and down values, sort of the activations of the neurons. And we put a constraint on the w, like a typical weight constraint. We constrain all the sum of the squares to the normalized sum of the squares to be 1. So we imagine we have this multi-dimensional, hyperdimensional sphere, and the weights all live on the surface of this sphere, and we're just choosing Gaussian random variables, and we're building this energy function. And this is called a spin glass. So where does this come from? What is this model, these spin glasses? What do we mean by spin? Where do the spins come from? The idea is that, imagine we have some spins, S1, S2, S3. And by spins, I mean they can point up. Imagine something spinning and it points up like this. Or it's spinning and it points down. So we have some object spinning that can spin up or it can spin down. So it's associated up or down. And we align them on a triangle. And we form an energy function H. And we would like the spins to be paired. So if one spin is up, the other spin should be down. So in this picture, S2 is up and S3 is down, so the energy is negative. J is less than 0. And our goal is to get all the spins paired. And the problem is that we don't know what to do with S1. If S1 is up, then it's paired with S2, but it's not paired with S3. And if S1 is down, it's paired with S3, but it's not paired with S2. So we actually can't satisfy all the constraints. We can't put all the spins in so that all the J's are negative. We can't pair all the spins. This is a concept called frustration. And this is critical to understanding what a spin glass means. By a glass, we mean a very, very large system of these sort of up and down spins that are very frustrated. There are lots of constraints that cannot be satisfied. Now, this is very different than what we typically have seen in convex optimization problems, such as SVMs or structural SVMs or more sophisticated convex optimization, where the goal has been to maybe you have a large number of constraints. Maybe you have even an exponential number of constraints. And the goal of convex optimization theory is to rewrite the problem, to relax the problem, such that all the constraints can be satisfied to some level of numerical accuracy. And that gives you a solvable problem. Now, it turns out in spin glass theory, you can have a system which has a massive amount of frustration. There's a huge number of constraints that cannot be satisfied. And yet, somehow, this also behaves as if it has some sort of rugged convexity to it. And this is the puzzle we're going to take a look at. Now, we have known for some time, this has been suspected in condensed matter theory. It was solved many years ago in the high temperature solution of the tap equations. In Lee Kuhn's work, they talk about more modern analytic solution of the entire problem. But the basic idea is that we've known for a very long period of time that in a p-spin spherical glass, the critical points are ordered. Meaning that as you go up, if you start at the bottom, the lowest energy, there's a ground state. And just above that ground state, there's a whole bunch of local minima. And they're all fairly degenerate. They all have the same energy. And they may all, in fact, be equivalent. Maybe any one of these local minima will do. I mean, that's sort of the current idea is that any local minima will do, so it doesn't matter which one you fall into. But they're all within some very close barrier to the ground state, some floor. As you go up in energy, you start getting critical points, meaning saddle points. They're not local minima, but they're not. They're saddle points in that they have a minima, but you can also get out of them. You can walk out. A good solver will walk out of them. You can design stochastic gradient solvers, maybe with momentum. Stochastic gradient solver with momentum, for example, might jump out of a saddle point. And as you go up higher and higher in energy, you have more and more saddle points. So imagine the opposite is we start at very high energy and we get to minimize the energy. As we go down, as the stochastic gradient descent solver is flowing through, it's jumping through these critical points and washing around washing all through them, getting to the bottom very quickly. So this has really been suspected for a long period of time. If you pick up an old book like by Duda and Stork from 1990 and neural networks, they'll talk about this. The idea that we've suspected for a very long period of time that very, very large networks, in fact, have no high-lying local minima. All the local minima are at the bottom. So effectively, these systems behave as if they're convex. Not perfectly convex, but they behave in the sense you can get to the bottom, and a good solver that if you have a good solver that doesn't get trapped in saddle points. So here's an example. I took this out of the paper Lee Kuhn published. And this is sort of the evidence for this. So anyway, what do we mean by the evidence? Phenomenological evidence. Well, on the left side, they're just simulations of a p-spherical spin glass, and you see it at different levels. You have 25 spins, 50 spins, 100 spins, and so on. As you increase the size of the glass, the distribution of the losses, the distribution of the energies in the spin glass becomes more and more Gaussian and sort of highly peaked. Likewise, if you run a neural network and you have 25 hidden units, a simple multi-layer perceptron, 25, 50, 100 hidden units, you increase it up, you see the same, just similar kind of behavior that as that the distribution of solutions, the ground state, the loss, it becomes very, very narrow, it gets very peaked. So this is essentially the evidence the empirical phenomenological evidence that suggests that simple multilayer perceptrons behave as if they are p-spin spherical glasses, and that in some sense, if you any of these solutions in the red, and if you're at the 500 hidden units, any solution will do, and you're just running this thing. It gets into a local minima. It never really approaches the ground state. It just gets trapped in these local minima, which are just above the ground state. And any of these solutions are pretty good solutions. And this is sort of the general picture that people have right now in a theoretical idea, understanding of how these methods work. Now, another piece of evidence for this, to believe this, is that in many networks, at least in the old days, and certainly in some cases now, you have to do early stopping. Meaning that if you run SGD, you set up something in TensorFlow. You run SGD for a few epochs, maybe 20 epochs, 30 epochs or so. But you don't want to go out to 100, 200 epochs. Because what happens is you go out too far, you reach the ground state, and the ground state is a state of overtraining. So you want to sort of get to this local minima, get there about 20 epochs, and you stop. So the picture sort of looks as if you run the epochs for a period of time, you stop the epochs, and the test accuracy is pretty good. If you run too many epochs, the test accuracy will degrade, even though the training set accuracy doesn't. And so this is the standard picture that a lot of people talk about. I think this picture is actually hard to regenerate. I think more what you see as you do early stopping is that both the test accuracy and the training set accuracy falls down. So the whole system will collapse. And I'm going to give an explanation of why that happens. And I think we have to be very careful when we start looking at this, that we be careful we're just stopping the epochs and not doing things like adding extra normalization, adding extra weight regularization. So this is the general picture that we have right now and people talk about. And what I'm going to argue is that this picture is a little difficult to actually generate in practice very, very carefully. And it may be true, it may not be true. And I'm going to present some ideas of rounds for how we can take a look at this in more detail, and some other models, and adding some more detail to our understanding of it to get a better handle of what's really happening. Nevertheless, the summary so far of the current interpretation: finding the ground state is easy, generalizing is hard. Finding the ground state is irrelevant. Really, any local minimum will do. And if we actually find the ground state, then we're in a state of overtraining. We want to avoid it. And this is our current interpretation of what's going on. Now, I want to talk about this in terms of the recent results in p-spherical spin glass theory. So the results really say that, and this is the research result 2013, the distribution of critical points, and what it says about the distribution of critical points and the concentration of the means. And this is a result about an isotropic random function on a high dimensional manifold. And what these papers are trying to say is they're trying to understand the concentration of the means. How do the variables concentrate when the weights are drawn from an isotropic random function? And we can talk about the specific mathematics of this later in another post if you want to dig into it. These results, even though 2013, are really related to some old results on something called the TAP equations. And the TAP solutions developed in 1977, and much later as research continued in theoretical physics and condensed matter physics by looking at the number of critical points, which is related to the TAP complexity. And the reason I bring this up is because for the TAP theory was originally designed in the high temperature limit. So it was the high temperature solutions. It was sort of understood that these models have a temperature associated with them. And as you increase the temperature below a certain point, the spin glass models would enter into a glass phase. And so it wasn't entirely clear what was happening in the glass phase. And it was always a case that even though you were studying the TAP solutions and studying these p-spin spherical glasses and related glasses, you were studying them in a high temperature case, not in the low temperature behavior of a spin glass. So in order to really understand what these models are really saying, what these papers are really saying, and the theoretical results, we have to look at understanding what glasses are. So I want to go back to the original problem we posed. What problem is deep learning solving? And I propose, well, we're just minimizing the cross entropy of the output layer. We just have this energy function, depends on this, and we just and it depends on these this complicated nonlinear thing t. Ti is actually is an output of a very complicated nonlinear function, and we're just minimizing it. So we just treat it less an arbitrary optimization problem. And I'm going to say no, that's not. I want to look at it a little more careful. I want to say that this energy is a combination of two things. It's a combination of entropy and it's a combination of energy. There are entropic effects. That is, we're not just minimizing an energy function. In fact, it's more like we're minimizing a free energy. What is a free energy? Well, in machine learning parlance, when we think about free energy, sometimes we think about divergences. This is, for example, what you might see in the theory of variational autoencoders. When you're minimizing the free energy, you're maximizing the divergence, or one or the other, and they're trading off each other. This is a typical modern form. To really understand this, I want to go back to an older model, probably something people forgot about unless you use scikit-learn. It's sort of stuck there in the neural network package, called the restricted Boltzmann machine. The restricted Boltzmann machine is an old model, 2006. It's sort of deprecated. There's a little bit of research going on now, but it's a really important model because we can really see everything. The restricted Boltzmann machine specifies an energy function. You have visible units and hidden units. And the energy function is just some bias times the visible units, A, plus some bias times the visible units, H, plus some coupling, VWH, which couples the visible to the hidden. And we typically say this is a bipartite graph, and all the visible units are connected to every hidden unit, but the visibles aren't connected to each other. The hiddens are connected to each other. It's a standard kind of the same kind of design you might see in a multi-layer perceptron, except we don't have any. When we usually solve a restricted Boltzmann machine, we have no labeled data. So instead, what we're trying to do is predict something, estimate something like the probability of observing a visible unit. In other words, if we're looking at the MINTS data set and we're trying to classify 1 versus 2 versus 3, we want to understand what's the probability of observing this data as a 1 or as a 2 or as a 3 and so on. So we say P of V is 1 over Z times the sum over H e to the minus VH, where Z is the partition function of the system. And it's a normalizer. And in this formalism, we can define the free energy directly. The free energy is just that object F, such that if I were to take e to the minus F of V, I would get sum over H e to the minus V of H. So in other words, the free energy is just this object which allows us to represent the probability directly as a sum over something. And this is actually all described in the original practical guide to training restricted Boltzmann machines by Hinton. So it's all there if you go into it. And what you get, if you work through it, is you get an expression for the free energy, F of V, which is minus V times the visible units times the bias, A, plus minus PJ xi, where xi is now the bias on the hidden, plus V times W. So we see the energy functions on the left-hand side. Then we have this other term, plus J, P log P plus 1 minus P log P, log 1 minus, P log P plus 1 minus P log 1 minus P, the cross entropy. So the free energy in a restricted Boltzmann machine is the sum of an energy term and an entropy term. And this is where I think we should start looking at models which look directly at the free energy and allow us to have a trade-off between the energy and the entropy. So I'm going to introduce such a model. It's like a spin glass model. It's like a p-spherical spin glass, but it's actually much simpler. It's actually the infinite limit of a p spin spherical glass, and it's called the random energy model. So in the random energy model, the probability, you don't have any energy function, you just have energies. We're just going to assume they're energies. The network, in other words, that the outputs, the energies that we get from the restricted Boltzmann machine, or maybe something else like a multi-layer perceptron or a very, very complex convolutional network, is just some random energy, and we're going to assume it's Gaussian distributed. You may recall, if we go back, sorry, I'll go back, that the energies are in fact, so this picture by Lee-Kun, that the energies were Gaussian distributed. So we're going to assume that in fact the energies are Gaussian distributed, and the probability of observing any individual energy is just 1 over z e to the minus beta e to the j. And there's a partition function, and we have this term beta, which is 1 over t. And beta gives us a scale. Beta lets us scale the energy. So it tells us what the size of the energy should be. Now, one of the interesting things about the random energy model, the reason I started thinking about this, when you look at this paper by Lee-Kun, and you look at the distribution of energies, these are the distribution of energies from the neural network. It can actually look like a plot right out of protein folding theory, where we're looking at the distribution of the ground state. And we see that the distribution of the ground state is actually governed by extreme value statistics, and this can be derived from the random energy model. And I see this in this plot from this very old paper from the Journal of Chemical Physics, and some paper probably in the 90s. And so you see what they call the plot of the foldability distribution is really just a plot of the ground state, the proposed ground state of a neural network. And so we can see that using the random energy model and assuming that we're looking at the actual ground state, and not these local minima, but the actual ground state, that we'd see something governed by ground state, by extreme value statistics. And it looks just like the plots coming out of these neural networks. So my point being that you can't really tell, looking at this multicolored plot, whether the ground state is a p spin spherical glass, or whether the random energy model is just as good of a model if your measure of quality, if your measure of what makes a good model is just seeing whether we can fit this plot. And moreover, this can be derived analytically. And at some point I'll write this up as a paper or a blog post and derive these results exactly. So we got to get back to this idea of temperature. What is this beta? Beta is a scale of the energy. Now, when I start introducing this, I need to make a point about something. There are a number of people, a few researchers in the field, who are starting to use algorithmic analysis to understand classes of problems. Like, for example, use statistical physics to study compressed sensing. And in this case, what they do is they introduce E of j as an objective function. It includes a loss function and a regularizer. And then what they do is you form the partition function, and you form a mean field theory, and you take the limit as n goes to infinity and as t goes to 0. And this allows you to study whether your algorithm, for example, does compressed sensing, does L1 regularization, give you the optimal solution of the compressed sensing problem. This is not what I mean when I introduce the temperature. I'm not trying to do algorithmic analysis. In fact, the temperature is a proxy for the regularizer. So how is that? The point is that the temperature sets the energy scale. So let's say that beta is 1 over t, the temperature. And so P of j is 1 over z e to the minus beta ej. Well, if E of t is the effective energy, let's say we just have an effective energy which depends on temperature. Then you can see that E of t is just E divided by t. So as the temperature goes up, the energy would go down. And as the temperature goes down, the energy would go up. So this, of course, the energy is proportional to the sum of the weights times the activations. So what we would find is as the temperature goes to 0, the effective energy would blow up. It would diverge. So in a neural network, that means all the weights would explode. All the weights would go to infinity, and that's not what we want. Of course, whenever we solve any of these problems, whether we're doing multi-layer perceptron, convolutional network, or even really a restricted Boltzmann machine, we usually have some sort of weight constraint. We don't want the weights to get too large. And that's what I mean by temperature is a proxy for weight constraints. By keeping the temperature above 0, we are effectively keeping, it's the same as saying that the weights cannot get too large, the scale of the energy cannot get too large, and therefore we're keeping the effective temperature of the system above 0. And this is a key idea that we see in the random energy model, and I believe is extremely important in understanding some of these deep learning systems. So temperature is a weight constraint. The traditional case would be weight regularization, max norm constraints or dropout, or in batch norm regularization. So the idea is in deep networks, we temper the weights and therefore the distribution of the activations and the local entropy. Now the random energy model is also a toy model for a real glass. So this is where we're going to have to dig into a little bit about theoretical physics and condensed matter field theory and chemistry to understand what I mean by glass. What is a glass? A glass, this is a glass. I have a glass with a liquid and I'm drinking it, and this is typically what we think of as a glass. But what I mean by a glass is I mean a supercooled liquid. Imagine taking the liquid in this glass of tea and cooling it, but cooling it very, very quickly. If we were to cool it very, very quickly, its specific volume the volume that it has would not shrink. In most systems, unfortunately other than water, which behaves opposite, most systems, if you have a liquid and you cool it, it will shrink. It will shrink due to freezing. So a metal, for example, it will cool. As you cool a metal, it shrinks. If you heat a metal, it expands. So there's a position, there's a temperature at which that occurs. And a liquid will become a crystalline solid. However, if you supercool a liquid, if you cool it very, very quickly, it will not actually lose its volume. Instead, it will sort of just get more and more viscous. More and more, as if imagine I have this water and I pour some cornstarch into it and I stir it and it just becomes thicker and thicker and thicker. And at some point, there's a transition. If you were to sort of look at this curve and you sort of take the right and left hand sides, the top curve, and you make a linear approximation, there's a point where the two curves cross, and that point is called the glass transition. So the glass transition occurs far, far below the melting transition, or really the freezing transition. There's a glass transition and there's a freezing transition in these systems. And the random energy model is actually a model which can be used to understand the glass transition. It's a model which displays a glass transition, and this can be shown analytically. So we're talking about modeling real glasses, structural glasses. So the glasses are one of the oldest known materials to man. I mean, glasses were made the ancient Egyptians. Basically, you take sand and fire and you blow and you get a glass. So glasses have been around since the beginning of civilization, and yet nobody really understands what's going on. So some properties about real structural glasses that are interesting. All liquids can be made into glasses if we cool them fast enough. In fact, even metals, even liquid metals can be made into glass if we cool them fast enough. The glass transition is not a normal phase transition. It's not a melting point. It's not a freezing point. It's not like what you have when you boil a liquid on the stove. It's not that kind of transition. It's not a sharp transition. The arrangement of atoms in a glass is amorphous. It's not completely random. So a glass is not a completely random system. Glasses are universal. It's a universal phenomenon, all over physics, and the molecular details affect the thermodynamics. So we would expect, this is a fundamental property that occurs in all physical systems, and probably occurs in many systems around information theory as well. And what I'm proposing is that it may occur in deep learning systems also. And the other thing to realize is different cooling rates produce different glassy states. And this goes back to, the Egyptians blowing. When you go to a glass blower and they blow a glass, they change the way it cooled. Part of the glass can be made to be brittle. Part of it's brittle and will break, and other parts are very hard. And that's the ancient art of glass blowing relies upon this very simple fact that different cooling rates produce different glassy states. So when we think about the glass transition, we can introduce a phase diagram. So a phase diagram is simply a two-dimensional plot. On the bottom is temperature, it's our energy scale. and on the left is we're just going to call this the phase. And what we find is that in a random energy model, there's an entropy density. So let's look at the entropy. And recall that when we look at the Boltzmann machine, that it has an entropy and an energy. And when you add them together, you get a free energy. The entropy, as you go from high temperature to low temperature, the entropy decreases, all of a sudden it decreases very rapidly, and then it hits zero. It actually collapses. So when the entropy collapses, when T is below the critical point, and this entropy crisis appears to be what drives the glass transition in a random energy model. So what does this mean in terms of looking at solvers? A lot of times we talk about looking at solvers on the energy landscape. We design solvers that can avoid traps. This is a great example of a blog post that showed the different kind of solvers. And the idea is this is a saddle point. And the idea, SGD is not a great solver. It can get stuck. But if you do something just to add simple momentum, or you do eta grad or RMS prop, you can immediately pass through the saddle points. And so you can avoid some of these traps that occur. And so what we want to do to try to understand the energy landscape, let's assume that we have a bunch of traps. We have this glass, this sort of glassy system, and there are lots and lots of saddle points, a spin glass, lots of saddle points. And let's say that as we're running our solver, we get trapped for a short period of time. Well, there are a number of transitions. We have to move from, we're stuck, and then the solver runs for a while and it drops out. So there's a time frame associated with moving from E to J to E to J minus 1, moving down the energy landscape. And we might assume this is reversible. In chemical theory, you would assume this is reversible. You could go up and down. Probably in a machine learning system, you go down. But there may be systems where you sort of oscillate back and forth for a while. In that situation, there's a classical result, which shows that for temperatures near the glass transition, the traversal times are slower than exponential. So what does that mean? By slower than exponential, think about how we solve when we do deep learning systems. We have, when we run SGD, we have an annealing rate. So we're changing the step size. And usually the step size that we change, we use an exponential decay for our step size. So even something like RMS prop, go back to before that when we just do simple exponential decay on the learning rate in SGD, and that learning rate decays exponentially. So what I'm saying is that when you're near the glass transition, that learning rate would have to be slower than exponential. You would have to decay the thing really, really slowly. In a physical system, like a protein or a polymer, this leads to a paradox. If we just have a traditional spin glass, and a protein, for example, is governed by a simple spin glass, because of this classical result, it would take longer than the known lifetime of the universe to find the folded state, to find the ground state. So in physics, this has been a real paradox. And in protein folding, this has caused a lot of stress. So this is called the Leventhal paradox. And the idea is that in a protein, you have sort of this string, this polymer, and it has to fold into these different configurations. And if it were just folding randomly, or if it were just a random spin glass, the folding time of a polymer would take longer than the known lifetime of the universe. So clearly, polymers and proteins are not described by simple spin glasses. They're not simple P spin spherical glasses. That's not what's going on. So what's interesting is that there's an old analogy in neural network theory between protein folding and something called hot field associative memories. And for anyone who really knows the history of deep learning, you know that before there were restricted Boltzmann machines, before there was backprop, there was a whole group of physicists and neuroscientists who studied hot field associative memories. And the idea was that the hot field memories would make that somehow proteins are natural machine learning systems, that nature has somehow learned the memory pattern of a protein. And it's used a mechanism that can avoid the glass transition. It has a glass temperature that's as low as possible. It's formed a system where that glass temperature is so low that it avoids the glass temperature entirely via energetics. So imagine, for example, you have a polymer, and this is a polymer, and it's just folding on itself. And these are just the configurations. And it's trying to fold. It's trying to find different ways. It's a string, and it's folding on itself. And if there are no connections between it, it just can do anything. It can be in any configuration. As soon as you start saying that the polymer has to have some connection point. So imagine that you have a string, and the string has to be tied together at a certain point where it sticks together. All of a sudden, this changes the amount of configurations it can have. So if you have something like a polymer which has lots and lots of connective points, it has points where it's sticky and it sticks together, then the entropy it can sample, it doesn't have as much entropy to sample, and it will immediately, its energy landscape will begin to funnel, and it will become ruggedly convex. So in the upper case, we have an energy landscape on a simple polymer. And in the energy landscape, it's fairly flat, and there are lots of local minima, and they're all sort of, equivalent to each other. As you start adding structure or layers to connection points where the polymer has to stick to each other, the energy landscape becomes convex. Now, of course, it's not perfectly convex. There are lots of little local saddle points, but the convex, it actually becomes convex. And so this concept is called minimizing frustration. So an example would be there's an old paper from condensed matter field theory. The left side is a system which is which has it's a disordered ferromagnet where the frustration is minimized, and this is effectively the energy landscape. And you can see the energy landscape is punctuated with this funnel where it becomes very convex. On the other side is a spin glass, and the spin glass has lots and lots of local minima, and the energy landscape is nowhere near as convex. So in the theory of protein folding, this is called the funneled energy landscape. And the idea is that because the protein has structure to it, because as it folds, there are points it has to stick together. As the protein folds, these points have to hold together. That reduces the amount of entropy it can really have. It creates energetics that are very favorable. So if we look at the energetics of the ground state, we take a random energy model, and we assumed before that the ground state was Gaussian. There was a Gaussian distribution of ground states. And then we make an assumption that there is an actual state, an actual ground state, which is very, very low in energy. And this ground state is much, much lower. It's strongly correlated. And it's so strongly correlated that the system completely avoids the glass transition. So it's no longer a random system. It's a system with very, very strong correlations. And what we see is if we sort of draw the density of states, the way in which the system can, the number of configurations it can sample, when you have this sort of native state of this ground state that exists below really the floor of the system that we talked about before. It introduces an energy gap which causes the energy landscape to become funneled. And so in fact you have a global ground state and very, very few local minima. And what this means is that there is a trade-off. There's a competition between the energetics of the system, the energy function that you're optimizing, and the entropy of the system, the amount of wiggle room that the system has to operate, how many configurations the network can be in. In our picture of before of spin glasses, what happens is there is this ground. Recall before there was a floor of the ground state and there were lots of local minima. But now you have that floor has been punctuated with very, very low energy solutions, which are determined by having an energy function which is very strongly determined. And what I'm going to argue is that in nature, that energy function is determined through evolution and the protein. In learning theory, that energy function is determined through the training data. That as you put labeled data onto a system, that labeled data changes the energy function and causes the energetics of the system to overtake the entropy and cause the energy landscape of the deep network to become ruggedly convex. Here's another nice picture, typical picture of the Leventhal parabolic, where we have a glassy surface. In deep learning, this would mean vanishing gradients. When you have systems where there are vanishing gradients, it means you're getting near the glass transition. The energy landscape is very flat, and you can't find the minimum. And it gets stuck. The system, we all hate vanishing gradients, and we try to clip them and get rid of them. In a funneled landscape, there's rugged convexity, lots of saddle points, and the energetics of the system takes over, and the solver, a good solver, like a good RMS prop solver, can find that low energy solution. Let me give you a very specific example now by looking at the energy entropy trade-off in a restricted Boltzmann machine. So I took a restricted Boltzmann machine and ran it on the MINTS data set. I'll put a notebook up on my GitHub repo which explains exactly what I did. I actually used the Julia package Boltzmann to do this because it allows me to both output the entropy and to add a weight regularization. So I'm using a very basic weight regularization, a weight normalization on this to keep the weights from exploding. And on the left-hand side, I'm plotting the entropy and the free energy as the system is being trained. On the right side, what I did was I just sort of took 200 points off the entropy so you could align it and see. And what you find is that in the RBM, the entropy drops much, much faster than the total free energy. And so, of course, we don't see entropy collapse. It doesn't drop to zero. Then you would be at the glass transition. You'd be terrible. But it does drop very quickly. And so we do see that there's a competition between entropy and energy, and that the entropy is dropping off very, very quickly. And this is what I think we would like to see in a very successful network, which avoids overtraining, is that as the system is being trained, that the entropy would drop off quickly, and that the energetics would take over and drive the system to the ground state. So I'm going to give a couple examples where I thought it might be interesting to look for this. We tried to reproduce some of these results. It hasn't been as fruitful as I'd hoped. Nevertheless, I'll present anyway. One would be dark knowledge. The idea of dark knowledge is that you take a network like a multi-layer perceptron, and it's 784 visible units, 800 hidden, 10 output. And you run it on MLP, you run MLP on MINTS, you get 146 errors. But if you distill it, if you run the distillation process of dark knowledge, you actually can train a network with the same entropy, the same capacity, but a better loss function. The distillation process changes the loss function, and you get less errors. So I think this would be a good candidate example for seeing where a random energy, a spin glass of minimal frustration, would start to play in, where the energy of the dark knowledge system, the energy of the optimization function takes over and reduces the test error. Another example would be where you have adversarial deep nets may also act like an energy funnel. Here the idea is you have one network which is generating fake data and another network which is trying to discriminate whether the data is fake or real. And so the discriminator, over a period of time, is learning a very, very complex loss function. Again, the entropy of the system hasn't changed. It's the same network. You haven't changed, you haven't added more nodes or more weights. It's the same network. It's just you're systematically learning a better loss function. So your energetics are getting better and better. So entropy disappears very quickly. Energetics takes over. You get a ruggedly convex surface. So let me give you a summary of this talk, sort of the ideas that have been presented, and where I'd like to take some of the work. I presented an idea called the random energy model, which is a very simple theoretical model, an infinite limit of the p-spin spherical glass, but it has temperature involved, so it has a glass transition. I discussed the glass transition, both the physical glass transition and what that transition would look like in a deep learning system, and related the idea that having weight constraints, keeping the weights from exploding, is analogous to maintaining a temperature, from keeping the temperature from going too low. And that allows us to, so the weight constraints are one way in which we can avoid the glass transition. I then introduced a new model, an extended random energy model called the spin glass of minimal frustration. And I argued that in this model, there's a trade-off between entropy and energy. And when you have a system that runs out of entropy very quickly, if the energetics can take over and you have a really good loss function, you can get a funneled energy landscape. So in other words, a combination of using weight constraints and a very good energy loss function leads to a ruggedly convex surface. Then I provided some examples. I sort of went through a simple example of restricted Boltzmann machine and provided a couple examples I think would be interesting to look at. One being the loss functions in dark knowledge, and another being adversarial deep nets. Well, let me thank you for the time, for letting me present this talk to you on why deep learning works, perspectives, some theoretical chemistry. And I would encourage you to please reach out, ask questions, make comments, and I look forward to hearing from you. Thank you very much.